Hello YouTube, I'm Hao Yang, and today I'm going to be explaining static equilibrium through topics. So first, what is physics? Physics keeps changing as we progress and make new discoveries. New theories don't just bring new answers, they also create new questions that might not have been made sense and viewed from the previous theory. This makes physics exciting and interesting, but it also forces attempts at defining physics into generalization about what physics has been rather than what it might be at some point in the future. So, who is Newton? Sir Isaac Newton is a great physics scientist and mathematician. Isaac Newton was born in January 4th of 1643 and died in March 31st, 1727. He is a physicist and mathematician who developed principles of modern physics, including the laws of motion, and is credited as one of the great minds of the 17th century in 1687. He published his most acclaimed work, Mathematical Principles of Natural Philosophy, which has been called the single most influential book on physics. In 1705, he was knighted by Queen Anne of England, making him Sir Isaac Newton. And now we use Newton's three laws of motion for their applications. They are known as inertia, the first law, acceleration, the second law, and reaction, the third law. So, what is static equilibrium? Static equilibrium have to separate into words to explain to you. Static means something is rigid, that doesn't move or have no acceleration. Equilibrium means all forces are equal. So, static equilibrium is a type of equilibrium in which rates of forward and reverse process are zero. That means it doesn't go anywhere. So, basically, we are all familiar with dynamic equilibrium, in which at the rate opposing processes are equal. Static equilibrium occurs when there is no exchange between reactant and product. So I have conducted an experiment on static equilibrium. This is the weight, 10 gram. That's the weight, 10 gram, if you can see it. And that's the pulley. And that's the retort stand to hold it. So, the aim of the experiment is to verify the net force in 2 dimensions on an object that is static, equilibrium 0. Static equilibrium 2-dimension force example. So I have 1, 2, and a down force. So 3 forces. An example of static equilibrium 1-dimension force, which means it only goes up and down, but they are all both static equilibrium. Collecting data, and these are the tools that we need, which is a protractor, 360 protractor, and a Newton scale, spring scale. So raw data. This is force A, which is the string, and force B, the other string, and force C, the down string. Pretend the forces is acting on this point, and we start 0 as here. And these are the data that I have collected. Weight is 10 gram. These are my calculations. If you wish to see it, please pause the video. Now I'm gonna move on. This is the second calculation, which means the previous one doesn't equals to 1. When you see that plus that equals 0, that's right. But this plus this, you don't get 1, so it's not right. Therefore, there's human errors. I set the human errors to 0.1 newtons, which I was right. I changed 0.6 to 0.7 newtons. As a result shows, it worked out. 0.536 estimated as 0.5 plus 0.5 equals 1 newtons, which is static equilibrium. And this is the proof. I done it by myself, not just copy from the internet. So this is the clear version if you want to see it. And this is the second calculation. Conclusion. Data in the table above shows that the forces are nearly balanced, which is, I mentioned that it's 0.53 if estimated with 5.4, which is over. An analysis of the horizontal component shows that the horizontal leftward component sorry about that pause, my mom just called me. So analysis of the vertical component shows that the sum of outward vertical components of A plus B nearly balanced to the downward vertical component of C. The vector sum of all forces is nearly equal to 0 newtons. But what about the 0.1 newtons difference between rightward and leftward force, and the 0.2 difference between the outward and downward force? Well, why do the components of force only nearly balance? Not exactly. Why is that not exact? The sample data used in the analysis are the result of measured data from an actual experimental setup. The differences between the actual result and the expected result is due to the error incurred when measuring force A and B. Sorry that it doesn't make sense, I'm bad at English. We would have to conclude that this is low margin of experimental error reflects an experimental with excellent results. We could say it's close enough for government work. So alternations, as you know, I have changed 0.6 to 0.7, which is 0.1 newtons difference, and these are references. Okay, that's it for today.